Our world is complex and dynamic. We're only just beginning to understand the impact that human activities have on its stability. If we are to properly understand the cause and effect relationships, we need mathematics. And one concern that affects us all is the weather. We now take it for granted that television, radio or an app on our phone will tell us what the weather is going to be. And while the decision to wear a coat, take an umbrella or cancel the barbie is important, for farmers, emergency services and energy companies, the accurate predictions of the weather has far higher stakes.
The sort of people that depend on these forecasts, agriculture of course because they're a climate sensitive industry, but there are others as well, so forestry, emergency services, planning for droughts and for floods as well. Also the construction industry, if they're planning big projects, then whether it's a wetter or dry year can change the timing of those projects.
And mathematics is at the core of our ability to predict those weather events.
Weather forecasts work by solving the equations that describe the flow of fluids, very simple equations like this, on a grid over the whole planet. And the key thing is the point at which you start, and you get that from the observations. The thing that's really improved is the way we use the observations to start the weather models.
When in 1922, Lewis Fry Richardson developed numerical weather forecasting, he envisaged lots of people scribbling down calculations about Newton's laws of motion as they apply to gases.
Today's numerical weather forecasts use the fundamental ideas that Richardson came up with back in 1922. Very simple ideas. You take the equations of fluid motion and they apply to air as much as to water. You solve them on a numerical grid that covers the planet. You start them from some observations and you go into the future.
Yeah, so the one that's classical is not very wet.
The equations are very similar, although we know a little bit more these days. The observations to start the forecasts are a lot better, and that's crucial. And the computers, of course, are a lot faster. He did it by hand.
There's a high reliance on maths, not just on day-to-day weather forecasting, but for longer-term seasonal forecasts.
Some of the models are doing very well at predicting 3 or 6 months into the future, and they can get 7 out of 10 years right in terms of saying whether it will be above or below median rainfall.
Today's sophisticated maths-based weather models means the accuracy of a Bureau of Meteorology's 7-day forecast is equal to that of a 3-day forecast 30 years ago. And our ability to forecast severe events such as floods has increased dramatically. However, beyond 10 days, the ability to accurately forecast individual weather systems using this method rapidly decreases because of chaos. It is now time to forecast climate, the average of weather. This is where seasonal forecasting comes in. Instead of just looking to the past as an estimate of future climate, scientists have been using mathematical models to predict the seasons ahead. A new tool in the armoury is soon to be released and is supported by the Australian Community Climate and Earth System Simulator Numerical Weather Prediction System from a partnership between the Bureau of Meteorology and CSIRO with the universities. The Bureau's POAMA combines traditional atmospheric readings with measurements from ocean, land surface and sea ice, plus simple observations to more accurately predict the next few seasons. Sometimes the predictions have huge impacts on human lives. How infrastructure can be built to cope with extreme rainfall like this requires an understanding of the maths of extreme events.
Well, most people have heard of the normal distribution, or sometimes it's called the bell curve in the popular media, and that's often used to model average temperatures, average rainfalls, in fact averages of any kind. We can't use that, however, to model extremes, so we rely on something called the extreme value distribution. What that allows us to do is it allows us to use whatever little data we have on extremes, heavy rainfalls or extreme temperatures, and it allows us then to make projections of how extreme we might expect events to be in the next 50 years, in the next 100 years, or in the next 200 years, depending on the application. So a give sampler is simply used.
Along with the Bureau of Meteorology, CSIRO statisticians and climate specialists are working to ensure the best information about the likely future frequency and severity of extreme rainfall at particular locations is available for planners and engineers to guide infrastructure.
So this is how we actually simulate It's important to be able to understand how heavy we might expect rainfall to be in the future, because we want to be able to design our infrastructure and protect our infrastructure against the impact of extreme rainfall events. So we'll call these long.
While long-term forecasts will never be perfect, the new breed of seasonal climate forecasts and extreme events modelling will give those who rely on an accurate prediction of weather conditions the best chance of coping with the uncertain future of our
We
planet.
do the same thing for the vector of longitudes. It's hard enough to model extremes for the current climate with the paucity of data that we have now, but we have some even more difficult challenges in the future. The most important of these, I think, is to fuse projections of rainfall and temperature extremes from global climate models with our current best models of extremes for the current climate in order to make reliable projections of what's going to happen in the future.
You're always trying to overcome the computing limits. Computers are not fast enough to do the things we would like to do at the moment. Parameterizing the small-scale processes that the computer models don't explicitly represent is a very difficult problem. Using the observations that we have most efficiently is a very difficult problem. And all of those things rely on understanding the mathematics and pushing the mathematics further.